Welcome to this new webinar about silica sand in the green sand. So we'll speak today about new sand and coarse sand dilution and silica quality aspect within our group of Dynamic Foundry group in India. And I'm pleased to present it today and show you some good aspect about silica sand dilution in green sand. Okay, first I will explain you very quickly the agenda today. So introduction first will be a short introduction about the green sand component. I will also speak about the sand changeover with both new sand and coarse sand, silica sand characterization, especially classification, fineness, and shape. Then after we'll speak about the silica sand usage in green sand and challenges. Why do we need new sand dilution? What is olitization, definition and the consequences? Silica and expansion aspect. Then after we'll speak about example of sand types depending on region. And finally, we will have also a short discussion about new sand and coarse sand difference for dilution in green sand and conclusion. Let's start with a reminder about the green sand component. Well, so you can see that we have four main components for green sand. And I'd like to explain you again to make sure that we have, we speak the same language, we are on the same wavelengths during the presentation. Silica sand is the support role, bentonite is the strength role, carbonaceous product is chemical and physical role during pouring, and the water is the activating role in green sand. First, speak shortly about silica sand. As you can see, the expansion of silica sand is a major cause of casting defect. And you will see today, we will really try to explain more about advantage and inconvenience of silica sand. But definitely the primary control for reducing sand grain expansion are selection of the right quality of new sand, and especially concerning the fineness, the purity, distribution, right quality of bentonite also is really a key role, and the proper bentonite addition and additives. Well, so that is the silica. And the second one is bentonite. Remember that bentonite works, in fact, because it is swelling. So when we introduce external moisture to bentonite, then you have a sort of swelling consequence, causing, in fact, explaining why we have a bonding effect between the grain of silica. So the water is really activating the bonding. And note that the swelling difference of natural sodium and natural unactivated sodium bentonite is quite different. The third component is the carbonaceous additive. As you can see, it is several roles that we can define with lustrous carbon playing, for example, a role of anti-veining agent. And as well, carbon particles generated, generating, in fact, a film deposit appearing between the sand and the metal. And with the effect of an anti-veining action, decreasing the risk of metal penetration. And another action is reducing atmosphere during pouring and the gas pressure balance from volatiles. Last point is the corking effect coming from the corks, compensating for silica expansion. And it's a good point to discuss that today because we will really explain the question of silica expansion a bit later during this presentation. And the final one, the fourth component, is water. Water is to activate the clay. Water is needed also with a high mixing energy to be efficient. And you can see here the link between the bridge between two sand grain with some bentonite. So green sand will have to withstand high temperature due to metal pouring, and water will be the first component to migrate and evaporate. So you have the binding, which is done with like clay and water bridging. So the next one, now I want to go to the second part of the presentation. What is the sand changeover? What do we need to maintain balance of green sand in a green sand system for iron or for steel? Green sand will be continuously modified during each cycle. And then the main objective of any foundry man will be to maintain the consistency. And new sand and coarse sand dilution is one of the main key to maintain this balance. What is the purpose? You want, in fact, to compensate the modification due to burning and losses of sand. Well, so that is easy to say, but a bit more difficult to do. And I want to explain the principle of changeover time for you to understand this part well. We want to define what is the changeover speed. Changeover speed, it is in fact a specific analysis which is needed in order to create the best possible forecast for each change of property in the sand plant. And what we want to do is to compensate for the modification of each cycle. And sometimes you have a rapid changeover of your sand system, or sometimes you have a slow changeover of your sand system. As you can see in the first example I want to show you, it is a rapid changeover. And you can see there in this graph, it is interesting to note that the orange line is showing, in fact, the saturation of new sand introduced in the system, and the green one, the losses that we get at each cycle of new sand or bentonite, by the way. And you can see in this example, for 60% changeover, you need 10 cycles, and for 90% changeover, you need 25 cycles. So to summarize, for 95% of system sand change, you need 30 cycles and 5 days, which is quite quick. Second example, the same way of explanation, you have the green curve showing what you are losing at each cycle, and the orange curve is what you are gaining at each cycle. That is quite slow. You can see that for 38% cycle, 38 cycle, you need 60, you get 60% changeover, and for 90 cycle, you get 95% changeover. And to summarize in this example, so you have 95% of the changeover achieved after 120 cycle, 28 days. So it's a slow changeover. So now, since we understand what is changeover and what is regeneration, we want to speak more specifically about silica sand. Why is silica sand most commonly used for green sand composition? In fact, 3 different basic answers to answer this question. First, it is very economical. Secondly, it is available in most areas in the world. And third, it comes in a variety of grades, from very small to very large, from very rounded to angulars. And you can find, in fact, a very large number of sand for various applications. It's easy, in fact. That is the main explanation of why we use it as #1 sand. However, you can see that the concentration in the green sand system is not 100%, because you get some other component in the green sand. And for example, you can see here that typically you will find the sand composition, the sand content in the grain sand to be between 75 and 92% in most foundry grain sand system. It can be even more or even less, but in extreme cases. And the rest of it, you will see, is in fact oolitic, active clay, carbonaceous, other fines, and water. And I will tell you more about oolitic a bit later. You will see, you'll understand what it means. Well, so that is the distribution, I mean, the typical composition, I would say, of grain sand. The next slide, I want to show you also that although silica sand is the preferred one, we have some other mineral types that we can use in green sand or for foundry of for I mean iron and steel. And the main one are chromite, olivine, and zircon. And you can see that chromite sand is a very dense and angular material. Olivine sand, it's another highly angular aggregate. And it's quite easy to find it also in nature. And the final one is zircon, a bit more difficult to get, a rounded material, quite dense, very similar to chromite. And what we will look after in the next slide, we'll try to understand what are the physical properties of sand, the structure of sand, and also the AFS grain fineness number and the screen distribution, and finally the grain shape. That is a good explanation of what we want to understand together. Well, now keep on sand classification and sand property. If we compare silica sand, chromite, zircon, and olivine, you would say that definitely silica sand is not the best. In terms of density, it is not the best. In terms of bulk density, neither. Sintering point is even the lowest. Thermal conductivity is not so high, but the cost is very low and availability is very low. Again, chromite, zircon, and olivine are alternative in specific cases that we want to keep as a solution for specific application. Well, now that we know that silica sand is anyway what we want to use, we have to accept some inconvenience. In terms of structure, you can see that silica sand, chromite, and zircon and olivine have different structure. For example, our silica sand that we want to use is a crystalline form from the quartz family. And the other one, you can see the schematic on it if you want to refer on it later. Well, now I want to show you the next slide where we speak about classification. Classification is really a way to define the grain fineness number for each sand, and especially silica sand, the one we are interested for. And you can see that each sieve will be from coarse to fine on top of each other, and it will correspond to the fineness of each level. And you can see that if we put sand on the top of the sieves, you will have a sieving effect. And the weight of each screen with the material that has been retained will define the level for each proportion. And that will allow to determine what we call the grain fineness number and the average size of the sand tested. An example after distribution of sand, you can see that we can find, for example, 3, 5%, 7%, 19%, 29%. You have a sort of distribution on each sieve. And knowing that, we want to have about 80% in 3 to 4 screen. And we don't want to have more than 40% on one single sieve for the grain sand. And at the end, on the next slide, it gives you a bit more explanation. You can see that typical foundry sand will have 3 to 4 sieve distribution, as I was explaining before, to produce better surface finish still provide adequate venting, and also reduce effect of sand expansion, and also improve strength. You can see on this example, we are mainly on 3 main sieve, and 3.5, I would say, and the distribution is quite well distributed. So the next slide will show you, in fact, another aspect, which is the Foundry sand green fineness definition, depending on type of metal and type of castings. And as you can see, well, so steel is generally poured with relatively coarse grain fineness sand, iron with a medium grain fineness, and copper to brass with a medium to small grain fineness, and aluminium really to the smallest grain fineness. That is really what we want here to show in this sketch. Well, so now another point is to understand the type of metal as well, the type of casting. The type of casting, you can see it from the largest to the smallest. Here also that will have an influence in what kind of grain distribution we want to select for a foundry green sand. And you will have from large casting to even very small casting or even artistic casting, the largest grain to the finest grain. Well, that is, I would say, a quick summary I wanted to show you. And the next one is, in fact, foundry sand and grain shape. Foundry sand and grain shape, you can see that we can define the grain shape between different names and round, rounded, subangular, angular, agglomerated is a simple way to classify the grain shape. What happens when grain angularity increases, in fact? Then the surface area increases. You have also the moisture and the clay demand increasing. It could be the same as well for resin demand for core. It will increase the clay, the resin demand, and because of the surface area. Sand grain as well tend to fracture more, and green sand expansion declines. That is a summary. And the next slide shows you a bit more details about that, about this classification of grain shape. You have the very angular, subangular, until the well-rounded grain classification. And you can see some corresponding picture there with angular sand and a rounded sand. You see, visually, we can see a big difference. Also, you have also a different way to classify the sand, such as sphericity, angularity, and you have a sort of table where you can define what is high sphericity, low sphericity, very high angularity to well-rounded. So it's a way also to classify sand according to region in the world and to correlate potentially to strength for core making or for green sand making. On the next slide, we want to speak now about new sand and why do we have new sand in green sand system? Why do we not recover green sand without any regeneration? That would be very simple, but we need, in fact, to have some cleaning effect. We want to make up for sand losses first due to sand carryout with casting and spillage and dust collection. So that is really, we lose about 3%, 5%, 2%, depending on castings. So that has to be recovered. We want also to maintain the sand screen distribution. Sand grains fracture due to heat and erosion. We want also to control the accumulation of oolitic sand grain. And again, I want to explain you what is oolitic for those who do not know what is the signification of that. And we want also to flush system contaminant from the sand. For example, resin-coated sand from core, fracture sand particle, silica dust, thin clay, thin dead clay, ash and environmental dust. Well, so this is what we want to do. And also, how do we manage sand grain expansion, and how do we manage sand segregation? That will be the next point we want to discuss. But first, as promised, I want to explain you what is oolitization. Oolitization, in fact, is a function of, it happens because of the clay accumulating on the sand particles. And how does that happen? In fact, above 500 degrees Celsius, so about 900 degrees Fahrenheit, in fact, the clay will lose the internal water, and the clay can no longer swell. It's like a transformation, a definitive transformation from clay to bricks. And then it will build as a brick around the silica grain. And that is a layer. We will create different layers of oolitization, oolitize, in fact, and that will change the green sand characteristic, because this part here around the grain is in fact very porous and also lighter than the grain, silica grain there. So it means the density of the grain, sand grain will change, will be lighter with more oolitization, and also the porosity, so the water demand will increase with the oolitization increasing. So that is interesting to know. And when enough of these layers are developed, we have a rather significant change in green sand characteristic because of the structure change. Well, now that you know a bit more about oolitization, I want to explain you the concentration of oolitization. That can change depending on the new sand system. And if you have a slow, I would say a high new sand addition, or both new sand and coarse sand addition, then you will have a very small oolitic buildup, and the concentration of oolitic in yellow there may be under 5%. You know, that will be something over even under 3%. In contrary, with a very low rate of sand turnover, then the oolitic buildup, because of the small addition of core and new sand, will be significant, and then we can account as a big part, such as 30% or even more of the total green sand composition. So that will change completely the way to drive the green sand. So the next slide will give you another problem about silica sand, show you another problem about silica sand, and it is the question of silica sand expansion. We must note that as long as we are under 100 degrees Celsius, 212 degrees Fahrenheit, then the silica sand expansion is contained. You have no expansion. But as soon as the water is lost in the green sand, then you will enter a phase where the silica expansion may become a trouble, and in fact, the temperature will begin to rise. As the temperature of the grain size continue to rise, then the sand grain expansion continues at an increasing rate. And the next slide is showing that, in fact, you will see that at 573 degrees, you have a very brutal change from a phase to another. So it's from alpha to beta phase. And there it is associated with a very big volume changes. And the next slide can show you even better, because we have a graph and also an explanation with a table. You will see that what is interesting, in fact, for us as a foundry man for green sand is this zone. The zone where, in fact, you change the quartz phase from alpha to beta. Why? Because this expansion is really huge, 1.5% in volume in 3 dimensions. However, it is reversible. So it means when the sand cools down, so you have the possibility to restart this expansion trouble at the next pouring phase. And that is, in fact, a transformation from alpha to beta. And it's, in fact, to summarize, it's a significant sand grain expansion that occurs at this transformation. And that must be managed. Why? Because that is really associated with expansion defects such as scabs, buckles, rat tails. Why? Because this volume change is really, really violent. So it doesn't happen in like a very regular curve. As you can see on this graph, it's not a regular increase like that. It is above 500, a very quick expansion defect with even a retraction after that. It's typically a bad effect for a risk of defect. Clearly, the expansion of silica sand is a major cause of casting defect, as I was just explaining. It's also the reason why we need proper bentonite addition and explanation of appropriate grain sand additive for the process. You can see that other sands such as zircon, olivine, chromite are much better for this kind of expansion. But also, again, they are not so available and very expensive compared to silica sand. Well, and the next slide will explain you a bit more the question of expansion defect. You will see that this slide is showing here on that side a metal arriving in contact with the green sand. And here the green sand, from the skin level in contact with the metal to further in the mold. Zone 1 to 5. We want to concentrate today on the zone number 3, where we have a saturation of moisture. Zone 1 and 2 are totally dry. All the moisture has migrated to the zone number 3, where you have a sort of saturated concentration zone of water. And what happens? You have here a very weak zone in terms of grain strength. And at the same time, between zone 1 and 2, you have the expansion of silica sand happening, creating some tension. That means that you have some tension generated there. And because it is the weak zone there, you will have some sand breaking there, generating expansion defect. And what is really interesting to know, it's a tensile force acting, in fact, in this region will be the cause of expansion defects such as scab, buckle in the casting. About a few millimeters there, maybe a few tenths of millimeter between zone 1 and 3, depending on the type of sand we have. We'd say between 1 millimeter and 3 millimeters, typically. Well, I wanted to show you that to understand the consequence of sand expansion defect. Now, another part of this presentation will speak about example of sand types depending on region in the world. And clearly, the quality of sand can vary depending on world region. You can see here visual example showing, in fact, difference between Indian silica sand, Europe silica sand, it's just an example, and USA silica sand. You can see that we have different angularity, sphericity, and chemical analysis that can show large difference. And I will show you some example now that we conducted in our lab some time ago. Here, for example, sand 1 from India, sand 2 from India as well, and from sand 3 from USA. By the way, in Asia, and especially in India, it's a bit more difficult to get high quality new sand for green sand production and core production. Well, so it is better to give an explanation and you will understand. Again, these three sands, we compared it for general data, washed water data, and unwashed sieve data. As you can see, you can notice big difference. So the sand 1 was a wet sand. Sand 2 was dried, and sand 3 was dried. And you can see that turbidity, it is the fine content in the sand. You can see that the sand number 3 is very low, 100. Here you have 1,600 and then 19,000. So the more, the highest the value is, you can judge, in fact, the contaminant in terms of fine content, ultra fine content in your sand. And you can see also some difference in volatile, loss on ignition, bulk density as well, as you can see here, with the highest bulk density for the USA sand, means less contaminant in it. And even more interested to look at the conductivity. The conductivity is really interesting to look at. You can see the low conductivity means usually low contaminant in the sand and low external elements having a potential effect on dilution in water, and especially ion dilution and source generation, creating some potentially some decrease in bentonite activation. Also, unwashed sieve data, so you can see some difference in AFS, but that is not so important. Okay, this sand is in fact coarser than this one, but the repartition, the distribution is the most important to look at, with a 3 to 4 sieve distribution, as I was explaining before. Well, now that we had a look at an example, I want to show you the same example with a characterization done with a cam sizer instrument. It's an optical camera that takes an image of every particle, and that can, in fact, classify sphericity, symmetry, or aspect ratio. And as you can see, for example, for the symmetry, it takes the shortest distance across the particle divided by the longest distance. And a value of 1 indicates perfect symmetry. As you can see, the sphericity of sand 1, 2, and 3. Here with sand 3, we are much closer to 1, showing that the sphericity is much better on sand 3 compared to sand 1 and sand 2. It's a good way to characterize the sand physical aspect in terms of sphericity, symmetry, and aspect ratio. Well, next slide now. Another very interesting comparison that we can do is the strength in green sand using bentonite. And in this example, we had 2 sand, Indian sand, US sand. And it was interesting to look at the different strengths obtained exactly with the same condition of usage. 7% bentonite, 93% new sand, 40% compactability, and the same mixing condition. And as you can see, here you have, in fact, the strengths, green compression strength, green shear, dry compression strength, wet tensile, before calcination, and here the same after calcination. And you can compare what we get with this Indian sand and with this US typical sand. As you can see, the difference with the same bentonite, same addition rate is huge. Just an example, look at green compression strength. From 100 to 128 is 28% difference in terms of strength. Look, another example, dry compression strength. 56% more dry compression strength with the US sand. After calcination, it's even more, the difference, even more. You can see that wet tensile strength, for example, is almost 100% higher with US sand compared to the Indian sand. So why to do that? It's just to show that depending on the sand you have, you may need a bit more clay for the same strength. Here, definitely, the only way to have the same strength with the Indian sand is to put more clay, and not only 7%, but maybe more, 8 or 9%. So that is I would say, a comparison to show you the importance of the sand type and the corresponding bentonite addition to obtain sufficient strength in a green sand. Well, now the next slide is really speaking about new sand or coarse sand. New sand or coarse sand for green sand regeneration and dilution. Is it better to use coarse sand or new sand? In fact, it is supposed to be quite equivalent, as both sand, coarse sand and new sand, will allow, first, to make up for sand losses, as I was explaining before, due to sand carryout and spillage and dust collection losses. Also, to maintain sand screen distribution. Also, to control accumulation of oolitic in sand grain, as I was explaining before, and to flush system sand from contaminants such as fracture or thin dead clay or etc. So again, so it's supposed to be quite equivalent. However, we can notice a difference for the question of to flush system sand contaminant from the sand if the resin-coated sand from core is in excess. Then, if it is in excess, it could reduce the bond efficiency, the bridging effect between sand grain, between bentonite and the new sand, in fact. In this case, depending on the foundry constraints, it will depend on each foundry, in fact. We may need to define the appropriate balance between new sand and coarse sand addition. For example, you may need to put, if you get 2 kilos of coarse sand entering, you may need to put 1 kilo new sand to compensate and have a balance. Or you may need to put 2 kilo new sand to compensate and balance. In some cases, you may need no new sand at all because you have sufficient dilution with the coarse sand. But again, no general rule, more a rule for each foundry, depending on each foundry constraints. So the next slide, again, will show you an example of cold box core to explain you the difference between region. Again, we notice a significant difference between Europe, USA, and Asian foundry, since new sand quality are different. An example for cold box core is the following. If you use typical cold box core in Europe or USA, typically you will need 0.5% resin and 0.5% MDI, generating a max quantity of loss on ignition of 1%. So it's not a high concentration. In India, for example, for typical Indian sand, you will need more than double in terms of resin quantity and MDI quantity. Means that you will have a loss on ignition above 2%. What does it mean? It means at the end, residual LOI after pouring is low in this case, and is medium to high in the case of high LOI due to resin and MDI. So that means that the residual LOI after pouring can be higher and may change your way you need to dilute new sand and coarse sand for green sand regeneration. Well, the next slide, if you want to know more about the green sand dilution with new sand and coarse sand, I would advise you, in fact, to look at this study. It's a study done in USA, and It's about green sand dilution by new sand and coarse sand addition. And again, if you look at the abstract, it is done with phenolic urethane, so cold box core, compared with new sand addition. So it's interesting because it's exactly typically what happens in most of the country. And to summarize the conclusion, we can see that the core, in fact, coarse sand can be successfully substituted for a new sand, and that under normal addition level, no detrimental degradation of mechanical property are expected. That is a general conclusion for USA again. However, you can note 2 points. First, if it is a core again with much higher resin than MDI, so you may not have the same logic of conclusion. And the second point is, for both wet tensile and friability, it is really related to how well the bentonite is coated to the sand grains, and it will be improved by additional milling and mixing time. So mold surface wash by the liquid metal stream was the only defect noted on disgusting pour from various dilution levels. So it's interesting to look at that. And you can refer to this study if you want really to know more about what has been controlled and how it has been controlled and how this conclusion has been defined. Well, so now we can arrive to the final conclusion about our presentation today. And I want to summarize it very briefly and make in a few bullet points. First, if you want to use new sand or coarse sand for green sand dilution, remember that new sand or coarse sand dilution is anyway necessary to regenerate green sand. Green sand cannot turn as ever without any regeneration. So you need a regeneration anyway. So coarse sand in general can be substituted for new sand. That is also a general conclusion we can have. However, a balance between new sand and coarse sand addition might be necessary depending on foundries. We may need to define a proportionality between coarse sand and new sand addition. Also, bentonite efficient coating on sand is very important, and milling time is playing a key role for maintaining wet tensile strength and friability at acceptable level. So that is really an important point to remember. And the type and the quality of new sand or coarse sand used for green sand dilution will strongly impact the green sand strength. And finally, the right choice of bentonite and additives will contribute to reach a well-balanced green sand. That is what I wanted to say as a conclusion. And well, now I think it will be time to have a potential discussion about this presentation. As you can see, the conclusion is wide. And if you have any question, any more explanation you would like, you will like to have from us and for my colleague, please don't hesitate to contact Vivek, Suru, Jejoras, Kuldeep, Shashi, or myself in India or other colleagues within other place in the world from MTI, and we will be very happy to contribute and to help and to give you some answer. Okay, thank you again for your time and for listening and for your participation during this webinar. And don't hesitate again to contact us. Thank you very much.